Okay, organic chemistry 2342. We're going to continue on with chapter 18, part 2. What kind of reactions can we do with these alpha carbons of the carbonyls? So one of the first reactions I'd like to share with you is we can actually do halogenation at that alpha carbon, okay? So we have a couple different ways to do it. Because we can form those enolates, because we can form that eno-keto-tautomerization with acid or base, we're going to use acid in this case to generate an alpha halogen, okay? So in the case of this acid catalyzed system, we end up getting a single replacement of one of the hydrogens in the alpha position with the halogen, okay? So let's look at the mechanism of how this works here. And if we look at this system here, if we start with our ketone, which is our more stable system, and we protonate our carbonyl here, we can get to the tautomer that gives us the enol right here. Once we get the enol, we can actually use the base that was created from that first step to deprotonate that to create our intermediate here. Then once we form this double bond right here, it can act as the nucleophile because it's electron rich to react with the bromine, kicking out the bromide minus and generating this new alpha bromo compound right here. When it does that, we now have a extra proton in our system that can be removed with water as our base to give us our alpha bromo keto compound. Okay. So if we undergo the same reaction but in base, we actually are going to end up replacing all of the alpha hydrogens, because as we do the system, the base still can remove the alpha proton and generate the system. So let's look at how that works right here. So if we have two alpha hydrogens on the system and we use an excess of bromine, we can actually get a geminal dihalide in the alpha position of this carbonyl, okay? So the reason it's a little bit different is because of the intermediate here, okay? Instead of deprotonating, instead of forming the protonated material first, we end up deprotonating first. Instead of protonating the carbonyl, we deprotonate first. And when we do that, we create our nucleophile on our carbon. That nucleophile can then undergo the tautomerization to give us the enolate, and then that acts as our nucleophile to react with the bromine to generate our material here. Once we've generated this compound here, we're back at that keto derivative, and then that means our base can interact and deprotonate the next hydrogen. Notice we don't have that mechanism available to us in the acid catalyzed system. We only have that available to us in the base catalyzed system. Okay, so how can we use that to our advantage? Well, one way we can do that is in a reaction called the haloform reaction. In a base-promoted halogenation reaction, we can take any methyl ketone right here and convert it into a carboxylic acid. Now, the way this works is that we will, using the base catalyzed halogenation at that alpha position, we can replace the first hydrogen, the second hydrogen, and the third hydrogen. Once we get 3 halogens on this carbon here, it actually becomes a very good leaving group because it have all the electron drawing of the halogens, allows it to be displaced as the anion, okay? So once we form the tri-substituted carbon here, we can have attack by the hydroxide to give us our intermediate here. And now we have a competition by which is the better leaving group. Do we have a hydroxide as a better leaving group, or do we have that tri-substituted methyl group? And in this case, the tri-substituted methyl group is the better leaving group. And then of course we have base in the system, so we end up with our alkoxide, our carboxylic acid anion, and then our halo compound or haloform compound. So that could be, if it was bromine, it would be bromoform. If it was iodine, it would be iodoform. If it was chlorine, it would be chloroform. Okay. So this is a really good way of making carboxylic acids from those methyl ketones. And it only will clip off methyl ketones because if you only have 2 halogens on there, it's still not good enough. Okay, so what's another way of doing this here is that if we started with a carboxylic acid, remember that doesn't form it as well. However, we can generate an alpha bromo compound to that system. And what's interesting is that when we do it, we use this halogen with phosphorus, which in the reaction mixture actually creates our phosphorus trihalide compound. And the first step in the reaction is actually the generation of an acid halide. So let's look down at this first step in the reaction here. And we start with our phosphorus compound and bromine, and so that generates the phosphorus tribromide. The first thing the phosphorus tribromide does is remove that hydroxide to generate our acid halide. Okay. Once we generate our acid halide, this now allows us to undergo our eno-keto tautomerization right here, allowing us to generate our nucleophile, our electron-rich nucleophile, which then can interact with bromine to generate our alpha halo and acid halide. Okay, so we've generated our compound here, and then it stops at that point right there. And when we work up the reaction by adding water, the acid halide is hydrolyzed off, giving us our alpha bromo carboxylic acid. Okay. We can also generate this kind of compound using the acid halide, and because we don't work up the reaction in water, we can maintain that acid halide while still generating an alpha halo compound. So in this case, we'll start with an acid chloride that we all know and love, and then this is what we call a succinimide, where we can have a halosuccinimide here. The most common one is bromine or N-bromosuccinimide. In this case here, we can use that to generate our alpha halo acid chloride plus a succinimide as our byproduct. Then we can go on to react our acid halide to form other compounds, but we'll still have that alpha halo compound. Okay, another way to do that is we can actually start with our acid halide again and just use iodine. Iodine is much more polarizable, and we typically do this in thionyl chloride as our solvent because that maintains our acid chloride here, but this is polarizable enough to generate our alpha iodo compound here. And so we can use these as really good intermediates for then reacting to make an ester or an amide with this, and then we'll have this alpha iodo compound to be nucleophilically displaced by some other reagent. Okay, so let's look at whether and how we can use these alpha carbons as nucleophiles or electrophiles. So one thing we can do with this halo combination here of generating this alpha halo compound here is that we can then, once we form this alpha halo compound or alpha bromo compound, we can then displace it using a nucleophile to give us an alpha addition product here. So we've actually started with our carbonyl compound. If we didn't have this halo compound right here and reacted with a nucleophile, it would attack at the carbonyl compound. But because we generate this alpha halo compound first, we can then displace that halo and generate our alpha nucleophilic attack site. So how can we use this to our advantage? Well, there's a couple different ways to do this. Oh, and we'll generate right here. For example, our electrophile can be anything. Oh, yeah. We can, instead of doing it with our alpha halo compound here and reacting with nucleophiles, we can actually use our base to deprotonate it and create our enolate first. Once we create our enolate actually can then react with our electrophile. And so our enolate here is our nucleophile there. And so we can react it with our electrophiles and generate our other compounds. So for example, we can attach an acyl group next to it here, or we can attach an alkyl group here. So whether we're looking to attack it with a nucleophile or an electrophile, we can change the reaction conditions to do either one using the same enolate intermediate. Okay, so how can we use that? Okay, so if we can generate this alpha halo acid, then we can attack it with any nucleophile we want, and it'll attack specifically at this alpha position. For example, if we use hydroxide as our nucleophile, we can get our alpha hydroxy acid generated from the system. If instead of using hydroxide as our nucleophile, we use ammonia as our nucleophile, we can actually get our alpha amino acid available to us that way. So this is a really interesting way to substitute just at this position while not changing our carboxylic acid and not having to protect our carboxylic acid. Okay. So what other reactions can we do here? All right, so we can use it as an electrophilic reaction by, if we used a strong non-nucleophilic base like T-butoxide, we can actually deprotonate at the gamma position here to give us our conjugated ketone, unsaturated ketone. Okay, but we have to have something very strong and non-nucleophilic like T-butoxide to be able to do that.